Okay, in this second part of these videos, we're going to talk about titration, and that's what we're going to talk about. And so titration, let's go ahead and define it. So we can define titration as analyzing a solution using information about volume. Sometimes you hear it called volumetric analysis. That's just another way of saying the same thing. And I want to point out, well, first of all, in this unit, let's remember that we're thinking of reactions in solution. So we use titration when we have solutions, things that are dissolved in water or other liquids. It's a way of analyzing a liquid, not a pure liquid, a solution. Another important word here is analysis. We're focusing in this unit on, in the whole course, on analyzing things, using information to find out something about what we have, or find out things we want to find out. That gets repetitive. Okay, in titration, we're going to use information about volume, and I'm going to talk about that using these pictures in a second. But you're familiar with analyzing solutions or solids by using information about mass. Last year, and even this year, we used the mass scale. You used it in your first lab to mass substances, and then from those, the grams that you find out how many moles you have, and then you use that in stoichiometry to find out how many moles you have of something else. So that's an analysis using mass. We're going to do something similar today, but instead we're going to take volume and try to find out about moles of something and how that relates to moles of something else using a balanced reaction. I know I'm not going to be able to, hold on. So I was able to make that smaller. So this second one, the volume to moles, that's what we're thinking about. And then sometimes, once we find the second amount of moles from our balanced reaction, we'll either translate it back to volume of something else or to grams. So this one is volume analysis. Again, molar relationships are key, and you see moles in the middle there. So titration is analyzing a solution using information about volume. This is a picture of a typical titration setup. You have a solution here, and the one at the bottom is what you want to find out about. So you may not know the concentration of what you have here. That's why it's called unknown concentration. This one happens to be an acid, but it could be anything. The lab we're going to be doing in this unit will be a titration not involving acids and bases, but it will be involving a redox reaction. But nonetheless, we'll have a solution that we do not know the concentration of. We're going to add a solution that we know the concentration of, and you add it in this funny thing called a burette that has little, you may not be able to see them, little tiny lines, and it allows you to carefully measure the volume of what you add, so you know exactly how much you added. That'll be important. In this particular titration, this is an acid-base picture, and they're measuring pH using a meter. We'll do that later in the year. But sometimes, when I was in school especially, we didn't have pH meters for everyone. We had to use a color change as an endpoint. And at the endpoint, and we're going to define what that is, the solution would change color. You see here it went from clear to pink, dark pink. A color change can be a sign that you've reached the equivalence point of your reaction. Let's talk about what that means. So there are two important words. Well, I think I'm going to define them when we work the problem. We have to define two words. One is equivalence point, and then endpoint. And what really happens is at the endpoint, your solution you put something in it that will change color when you get to your endpoint. I'm going to define these words in the next problem. They'll be more meaningful then. So here is a sample problem for an acid-base titration. That means an analysis of an acid or a base by measuring the volumes that you mix together. And one commercial method used to peel potatoes is to soak them in sodium hydroxide solution for a short time and then remove the potatoes and spray off the peel. The sodium hydroxide concentration is normally 3 to 6 molar, and the solution must be analyzed periodically, I suppose to make sure that it stays 3 to 6 molar. In one such analysis, 45.7 milliliters of 0.5 molar sulfuric acid, H2SO4, which is a strong acid, you need to memorize that one, is required to neutralize 20.0 milliliters of sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? I thought this was interesting. I did not know that was how they prepared the potatoes. It actually kind of grossed me out. But anyway, let's look at what we have here. We're told that we have a neutralization, and we're dealing with sodium hydroxide and sulfuric acid. So we're going to write, they're going to react. I'm going to write NaOH plus H2SO4. I look at these, this is a base, this is an acid. I'm going to write a reaction predicting what happens. Pause it, you write your products, then check. So here's the equation with the products. You're going to make water and sodium sulfate. You need two, every sodium ion has a +1 charge, so you need 2 of them to balance your sulfate. Now I'm going to balance the whole, so I wrote my products correctly. Now I'm going to balance the whole reaction. I have 2 sodiums here, 2 there. Now I have 1 sulfate group and 1 sulfate group. We have 2 hydrogens here, and I have 4 hydrogens on this side. So I'm going to put a 2 here. That gives me 4 hydrogens on both sides. I'm going to count my oxygens. I'm going to count my oxygens that are not in the sulfate group, because I have 1 sulfate group here and 1 sulfate group here. So I'm going to count the oxygens in these things. I have 2 oxygens here and 2 here, so I'm balanced. Okay, so let's think about what's going on and what we're asked. We're first going to write down what we need to find out. And what is the concentration of the NaOH solution? So we need to find out our unknown molarity of our NaOH. And we know that molarity equals moles over volume. And we know the volume of the NaOH. We know it's 20.0 milliliters, which is 0.020 liters. So, just keeping going here, if I can find out my moles of my sodium hydroxide, then I'll be able to use that to find the molarity, which is what I need. So I've started to figure out a way to find my molarity. I need to find my moles of my sodium hydroxide to get this, which is what I need. What am I given? I'm given 45.7 milliliters of 0.500 molar sulfuric acid. So let's write that over here. We have 45.7 milliliters. I could have written over here that I had 20.0 milliliters of this. 45.7 milliliters of 0.500 molar sulfuric acid. So, let's switch to a different color. If I can find out how many moles of sulfuric acid I use in this titration, then I could find out how many moles of sodium hydroxide it reacted with, and that's what I need to find here in order to find my molarity. So I'm going to try to find this. How many moles of sulfuric acid I have first? Well, I know I have molarity and I have volume, and I know that molarity equals moles over volume. So molarity equals, I don't know moles, but I'm given volume, eraser, blah, 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 0.0457 liters, because this is 45.7 milliliters, 45.7 milliliters, hoping you're getting adept at these conversions, multiply by 1,000 milliliters under 1 liter, and that equals 0.0457 liters. That's my volume. I don't know my moles, but I did know the molarity was 0.0, right? No, eraser. 0.500. So I can solve for my moles if I multiply both sides by 0.0457. So I'm going to do that and get moles of H2SO4 equal 0. Kind of in the dark here, 0.2285. 0.2285 moles of sulfuric acid. Okay, time to whip out the old BCA table, before, change, and after. Before, change, after. Except I screwed up, I need to write it under my things. So let's see if this will let me erase. Oh, it did, how nice. Okay, so I know that I am going to use 0.00285 moles of sulfuric acid. So that's my change. That's what I'm going to use. 0.02285 moles of sulfuric acid over here. That's why it's under the sulfuric acid. So if I use all that, that's what I started with. We don't really. And none is left over because all of this, oh, didn't mean to do that. All of this will react with all of that to neutralize it completely, so there's no hydroxides left over. So, sorry. So this is where I have to look at my molar ratio. And so we have to calculate if we are going to have use this many moles of sulfuric acid, how many moles of sodium hydroxide will that react with? And that's the same as always. So using this BCA table is not changing anything that you did last year. It's just adding an extra way to keep track, which will come in handy later on. So if we are going to start with 0.02285 moles of H2SO4 using the train tracks, but we're going to multiply that by a molar ratio. And the molar ratio comes from the coefficients. For every 1 mole of H2SO4 that we have, we need 2 moles of NaOH. These moles cancel, so now I'm going to multiply 0.02285 times 2 divided by 1 to get how many moles of NaOH I will need. I'm just going to write that over here because I ran out of room. And we will need to use 0.0457 moles of NaOH. So that's what will be used up, 0.0457 moles of NaOH. So if we're going to use that much up, that's how much we had to start with, 0.0457 moles, which is very important. That's how much sodium hydroxide had to be in our container. And so that's how many moles of NaOH we had to start with. That's this number. That's what we're looking for. How many moles of sodium hydroxide did we have in our 20 milliliter container? Now we can plug that in here and solve for a molarity. We had 20 milliliters, or 0.02 liters. Now we found out how many moles was in that amount. So let's go ahead and do that. I'm going to do it over here. So our molarity equals 0.0457 moles of NaOH over our 0.020 liters, 0.020 liters. And we're going to divide and find out the molarity of the sodium hydroxide solution. So that's divided by 0.02. So we found out 2.285 molar sodium hydroxide is our molarity. We're going to round that to 3 significant figures because that's what we're working with. So it would be 2.29 molar NaOH is the answer we would write and circle on our paper. So that's the molarity. Now I said I would define endpoint and equivalence point. So let's do that. So the point at which you add exactly enough sulfuric acid to react with all of the sodium hydroxide that you have, that is your equivalence point, because that is when you have added an amount of sulfuric acid that is equivalent to the amount of sodium hydroxide so that all the sodium hydroxide can be used up. So you have amounts of each. You've added enough of the sulfuric acid that it will react with all of the sodium hydroxide that you have. And it's really these protons that are reacting with these hydroxide groups. We call that the equivalence point. So I'm going to move to the next. The equivalence point So the equivalence point is the point at which you have added exactly enough of one solution, the solution that you're adding, exactly enough of that to react with the amount of the second solution that you have in your beaker. That is the equivalence point. There is another word called endpoint. An endpoint, the endpoint of a titration is always slightly after, just a millionth part after the equivalence point. Because once you've added, and this will be clearer when we do our lab. So I think I will just define the endpoint when we get to our lab, because it's going to be hard just to talk about it. But the equivalence point is very important. It's the point at which you have added exactly enough of one solution to react with the amount of the second solution that you have. And when you reach the equivalence point, that's when you can find out how much of the second solution you have. The end. Actually, not the end. So I think the third problem that we have on your notes, I'm going to work in class, because these are 2 long videos you've had to watch. So we will do the third one about the silver chloride titration in class together. So this is the end of the videos you have to watch for Monday.